we can use our potential formulas to find the energy of assembled charges. This looks like something that we just make up to make you do because it's a sadistic thing and it just makes hard homework problems. But it really isn't, okay? This actually is a fairly important fundamental thing that physicists and chemists think about. I mean, what is a molecule after all? A molecule is a bunch of assembled charges. So if you're working with some theoretical package and it makes a molecule and you think, does this make sense, or do I need to sort of call the people that write the software and say, maybe not, right? Because you see this thing of this molecule's assembly of charges, you might look at it and in your head you want to think a little bit about, is this high energy or low energy? You know, is it realistic that this would actually happen, or would this thing just fall apart? Or maybe it'll put it together in a way you'll say, oh yes, that makes sense. These would come near this, these would come near this. So when we think about matter, we often do look at assemblies of charges and think about, do they make sense? So what I'm showing you here isn't just to be mean. Okay? It's a little bit to be mean, but it's not only to be mean. Okay? So let's calculate an assembly of charges. So what we're going to work with is 4 charges on a square. 1, 2, 3, 4. Just pretend that's a square. 1, 2. It's a perfect square. I don't want to hear about it. It's perfect. It's a square. And this is Q1, Q2, Q3, and Q4. And the sides of these square are A. Okay? And we want to know, what energy did it take to bring all these charges together? Let's see. So there's sort of 2 ways to do it. One way is the sequential way. I'll call it sequential. Yeah. I'll write it where you can read it. And the idea is, when these charges were really far apart, they weren't interacting. They were all at infinity from each other. There was no potential anywhere. Potential was sort of 0 in this place because the charges are so far apart. So one way to think about it is you bring them in and you say, how much work did I have to do? What is the potential of bringing them in? Okay? So let's place Q1. What potential energy does that create? How much work did I have to do to put Q1 here? When nothing else is here, the answer is nothing, 0. It's just an empty universe, the potential is 0 everywhere. Bring a charge here, it sits there. I don't have to worry about it feeling anybody else's potential. Okay? Let's place Q2. Okay? So Q1 is now sitting here. It's there. Let's bring in Q2, bring it from infinity and bring it up to here. Well, we know the potential that it's feeling, right? The potential created by Q1 is being felt by Q2. So we know that potential is K times Q1 over the distance. But here we're asking about the energy, not the potential. Okay? So this thing's creating a potential, Q1 is feeling it, so really we care about the energy. It's like, how much work do we have to do to bring Q2 here? We multiply the potential times the charge Q2, the one we brought in. Okay? So the delta U is actually, you write sort of the potential due to Q1, K Q1 over A at this point. That's the potential there, but the charge we brought there was Q2, so you put a Q2 here. Okay. Remember, the potential is the energy per unit charge, and we multiply it by the charge. And now we have the energy. All right, so far it was free to bring in the first one. Bringing in the second one kind of had to push a little bit against the first one. Now let's place Q3, say. Okay. How much energy? How much potential energy do we create? When you're bringing Q3, it's now pushing against the potential due to Q1 and the potential due to Q2. Right. So due to Q1, again, it's K Q1 over A is the potential, and then times Q3. So again, it's at a distance A. But it also feels the potential of Q2. We had to work against that and create some potential energy here. So that is the potential created by Q2, K Q2 over, now it's not A, now it's the square root of 2 times A. Do Pythagorean theorem there. square root of 2 times A, and then that's the potential. We got to multiply it by Q3. So the two terms to bring in Q3, if we do it in this order, are both potentials created by the other charges times the charge Q3, because that's the one we're bringing in. And then let's finally place Q4. The delta U for Q4, now we're bringing it all the way in. We've got Q2, or Q1 is now farther away. Q1 is at the square root of 2 times A. So that's K Q1 over the square root of 2 times A times Q4 plus Q2 makes a potential K Q2 over A, it's only a distance A away, times Q4 plus K Q3 at a distance A times Q4. Yikes. That's a little messy. I think you can see it. Each time we bring in a new charge, it's got to push against more charges. That's why the first one has 0, this one has 1, this one has 2, this one has 3. All the K's are KE's. They're all Coulomb's constant. I'm sorry. Right. So the total energy to create this thing, if we call this sort of U1, U2, U3, and U4, so the total energy is just delta U1 plus delta U2 plus delta U3 plus delta U4. That one was 0, was right here. Okay. So you just add them all together. And it makes a mess because we've got to write, what is it, 3, 4, 5, we've got to write 6 terms. So it's kind of ugly. Let's do a little shortcut. Let's let Q1 equal Q2 equal Q3 equal Q4. Let's just call them all Q. Let's say they were all the same magnitude in the first place. If I'd have done that at the beginning, this wouldn't have made a lot of sense. I mean, it made a huge amount of sense as I did it, right? But it would have made a lot of sense if all those subscripts were missing. But now that we've done this part, let's let all the charges be the same. And if we do that, then every one of these terms is going to be just Q squared. Right? Q1 times Q2, they're both just Q. Q squared, Q squared, Q squared. Everything's Q squared. Everything's got a K in it. And the only difference is whether there's an A in the bottom or a square root of 2 times A in the bottom. There's really only 2 kinds of terms. So we can then just say that the energy to assemble them equals how many of the KQ over A's. It looks like there's 1, 2, 3, 4. 4 times KQ squared over A. And then how many of the square root of 2? It looks like just 2. Plus 2 times KQ squared for the square root of 2A. That's actually the answer. Let's see, I can make it a little prettier. Why bother? So let's see, well, okay, we can get rid of this square root of 2, and that could be the square root of 2, right? If we wanted to, you could simplify it a little bit. Not much point. Okay, then you could add 4 in the square root of 2. Okay, you can keep going. But the point is, that's the energy. Now that was a lot of messing around to get that, okay? So let me show you, there's another way. You don't just have sequential. The other way is to simply, is just to add. Add each, no, I'm sorry. The one word is pairs. You add up the energy for each pair that you can identify in the assembly. So here the sides of the square are making a lot of pairs. You just need to add that. So there I've drawn a line for every pair in this setup. There is nothing else. Okay. So now we just add the energy for all of them. And since we have the Q's the same and the A's are same, basically these 4 are the same. Okay. So the energy for each one of those is 4. And the energy is KQ. One of the charges makes a Q over separation A, but then you multiply it by the other Q, so it's squared. And then there's 2 of these. Right? Each one of these is 2K. It makes a potential KQ over the square root of 2A, but then you have to bring the other charge in, so that squares it. And then you're done. So it's actually quicker in most problems just to count the number of pairs. Even if this were in 3D, if it were a cube in 3 dimensions, you start counting all the pairs and all the way across in the cube. If we added one more here, you would just have to add all of its pairs up. You'd be done. Okay? So it's actually easier to do it this way than that way. So this looks, again, this looks like a sort of torture device for making hard homework, but it actually is fairly fundamental in a lot of things we do. There's another way we could make this problem interesting, or use this problem, is then ask the question, what if they were let go? What if we said, okay, it is symmetric, all the charges are the same, they're all Q, they're sitting on a square, you did all that work to bring them together, now release them all at the same time. What's going to happen? Well, if everything's perfectly symmetric and you're really good at releasing them at the same time, they're going to fly off in those directions. And you could ask the question, how fast will they be going when they get to infinity? When they're so far away, they're not really interacting anymore. How fast are they going? Well, what you've done is you've converted all that energy back into kinetic, or not back, we've converted all to kinetic energy. So you could take this thing and you could say this energy, each one gets a fourth of it, and it's going to turn into kinetic. And you can figure out how fast they're going. So this is a real conceptual thing, but it's useful to help keep us thinking about energy. As we think a little bit about real devices in electricity and magnetism, it's important to think about potentials and metals. You notice as we talk about potential, I keep mentioning volts, and that's really the common word in electricity, right? Volts and voltage, and what's the volts? And the other thing we have to have is conducting wires. Metals are very critical to circuits, and the reason circuits work the way they do, partly, is because metals do what they do. So let's look at the potential of a conductor. And again, by conductor, I mean something with freely moving charge in it, metal being the most common conductor. I'll slip up and say metal a lot, but I'm trying to be general since this is physics and say conductor. So we talked about the electric field around a conductor. We said if you have just a charged sort of piece of lumpy conductor, doesn't matter too much the exact shape, and if you put charge on it, we talked about what's going to happen is in a conductor the charges move so that two things are true. Basically they'll move so that E field equals 0 inside the conductor. So the charges will build up on the surface in whatever arrangement they need, whatever density of surface charge is necessary to make E equal 0. It might not even be constant. They can build up in certain regions where they're needed. The surface charge density can change over the surface, and it can respond. If you have a big negative charge out there, then that'll suck more up here. So it's not like some uniform charge density. The reason it can be so versatile and make the E field 0 inside is it'll move and do whatever it needs to do to make the E field 0 inside. And also, the E field is perpendicular to the surface, right at the surface. Okay? So you can have 0 field everywhere, and then right when you get out, there's your field. And you can have a field on the outside like that. But it's always perpendicular like that. Okay? That's what we learned when we thought about the electric field and the way a metal behaves, or a conductor behaves. Now, let's see, what does potential tell us? Well, delta V, I can't even write it anymore. Delta V from A to B is minus the integral from A to B of E dot ds. Right? So let's see, what does that tell us? Well, if we go along the surface, if we put our A and our B on the surface, say we start here and we go to here, our little ds's are always going to be in the surface because we do that integral, right? There's your ds's there, and the e's are always going to be perpendicular. So if we go along the surface, E is perpendicular to ds. So delta V is going to be 0. Any 2 points you pick on this surface and move around in all 3 dimensions, you're never going to get a difference in potential. So what that means is that the potential is constant on the surface of a metal. If one part of the metal or the conductor is at 9 volts, the whole thing's at 9 volts, if you're in electrostatic equilibrium. Okay? We can even say a little bit more. What if you go inside? What if you're at A and you go and put B there? Okay. Well, now you can have your DS's go in other directions than the surface, but the E field is 0. Okay? So DS can be whatever it wants. If the electric field is 0, then delta V is also going to be 0. So the potential is constant on the surface and inside the metal. Conductor. That's really all we need to know. But that's very important. That means when you have a wire and you hook it to some power supply, and the power supply is supposed to be at 10 volts, then you know that entire wire is at 10 volts. That's the point. That's why we use metal wires, because metals are very good conductors, and they keep this condition true. If I put this side of my wire at 10 volts, I know that side will be at 10 volts in electrostatics. We'll see what else can happen later.